Thus far, we've talked about ionic bonding and how different ions come together to form a compound. We're going to talk a little bit now about metallic bonds and the properties of metals and how they can be attributed to the way that they're formed. One thing to keep in mind is with metal bonds and metallic bonds overall, the compounds that are formed as a result are named the same way as ionic. Okay, so what we have down here in this diagram is just a little bit of a picture about how these things come together. And we're going to talk about those and why metals act the way they do. Like I mentioned, the formation of a metallic compound is very similar to that of an ionic compound. And what I mean by that is different metal ions will actually form. Like, for example, you might have lead that will combine with, say, chlorine. Lead is a metal, and it does have a charge. And so when we're talking about metallic compounds here, in terms of how those pieces come together, they come together the same as ionic, and they're named the same as well. You would call this one here, what forms is PbCl2, and that would be your lead 2 chloride, if I can fit it into space here. The bond, however, is very much different, and it has to do with how the electrons are arranged and how they are related to the nucleus. Okay, and the whole idea behind how these metals form is called the Electron See Model. And again, the Electron See Model will apply to metals. Now what we're dealing with here are the two major components. We're dealing with the nucleus and we're dealing with the electrons. Now typically, and as is the case when we're talking about ionic compounds, all of the electrons of the atom are going to be bound to the nucleus, or going to have a certain attraction to it. But metals, it's a little bit different. When we're talking about metals, what ends up happening is your nucleus, your core, maintains the structure that you see. The picture over at the right, you can see that there is a certain amount of structure associated in organization with this whole scheme. The difference, however, between a metal and an ionic compound, or something that normally forms, is that the electrons are not necessarily bound to the nucleus. And as they are not bound to the nucleus, they tend to just kind of roam around in the area of the nuclei. And so one electron might spend some time around one nucleus, but it might also spend time around another. The term that we use for this is that the electrons have been delocalized. So they're not locally located on one particular atom anymore. They tend to be shared amongst all of them. The adage that I always like to think of is that it takes a village to raise a child. Well, all of the nuclei are looking after all the children electrons. When a metallic bond is formed, what ends up happening is that we have cations, that's the positive nucleus, that happen to be positive because their electrons tend to be moving around from one side to the next. And so you end up with a swarm of electrons that'll tend to move and shift within the metal and take on a negative charge, and you have the positive that's left behind. Well, that positive is what bonds to, say, a normal anion, and a metallic bond is the result. Again, it's similar in that it will cause a charge to take place, but it's not the same in that the way that the atom actually looks. Remember, with ionic bonding, it's a direct transfer of electrons. There's no transfer of electrons taking place with a metallic bond. Instead, what is happening is the electrons are shifting, and as the electrons shift, it causes a charge to occur at the atomic level. The arrangement of these delocalized electrons gives metals the properties that they have. For example, in the diagram that we have here, we are going to be exercising and showing how metals exhibit that property of being malleable, able to be flattened. So when you hit a metal with a hammer, what ends up happening is you're not fracturing that crystal lattice structure that an ionic compound such as, say, salt has. Instead, what you're doing as you apply pressure here, or you apply pressure here, is you actually cause this whole top section to shift along that line. This shifting causes more compactness and thus malleability. Another property that we deal with metals is a large variance in their melting points. So a big range. There's a big range of melting points in metals. but on the whole they're very high. Now boiling point's a different story altogether. Almost all metals, the exception being mercury, are in the solid state. Therefore, the amount of energy that we're talking about to approach these boiling points is very, very high. And we're providing so much energy that we actually create less variance because we're talking about a tremendous amount of energy required to get these things to the point where we are causing a change of state of matter. Now, conductivity, both heat and electricity, can be attributed to the movement of the electrons. So because electrons are able to move freely, they're not bound to any single nucleus, the free-flowing electron, the electron fluidity, causes good conductivity of heat and electricity. The last thing is that most metals tend to be hard. Okay? The strength of a metal, however, is determined by the number of delocalized electrons. The higher the number, the harder they are. One fine example is that of sodium. Sodium is a very, very soft metal. And it's very, very soft because sodium itself has only one valence electron, one delocalized electron. And as a result, it's much softer than something, say, like copper. The last thing we're going to talk about, we've hinted upon this earlier this year, is alloys. Alloys are a mixture of metals. Think about them as a unique blend. When you're cooking, it's always the right idea to get the right amount of the ingredients. If you add too much salt, you're going to take away from the taste of your food. If you don't have enough, maybe you're always going to be a little bit bland. It's right to get the right amount. Alloys is that unique blend. That unique blend that brings about the best properties of all the metals included. Some commercial examples that you've heard of are steel, stainless steel, brass, cast iron, sterling silver, bronze, etc. That's all about metallic properties and bonds. Tomorrow in class we will be looking at comparing these to ionic and also to covalent.